Hello everyone, welcome to my master thesis presentation. It's my pleasure to present my work to you, and thanks in advance for your time. So I did my master thesis in Nokia Bell Labs, France under supervision of Ludovic Nohary and Rémi Barlot, and my tutor at Sorbonne University was Professor Sébastien Tixoy. And my project is called as Monitoring as a Service for IoT Networks. So first, let me give you an outline about this presentation. First of all, I'll give you a brief introduction about IoT network context and more specifically IoT network monitoring. Then I'm gonna talk about the researches that have been done until now about this context, so it can be a state of the art for my project. And then I'm gonna describe the requirements for our platform. And so based on these requirements, how we design the architecture. And also then I will describe the implementation of our platform. And then I talk about two different use cases that we implemented with our platform. And finally, I'll give you a brief conclusion about this presentation and talk a bit about the future work for this project. So all of us are surrounded by billions of IoT devices. From individual lives to industries, everyone is using this technology and our lives is affected by this technology. So it is obvious that the problems of IoT technology should be solved to help this technology to survive in the future. As you can see in this feature, in 2016, there was less than 10 billion devices in the world, and it is estimated that in 2020, this amount reached about 50 billion devices. And finally, in 2030, it is estimated that it can reach over 1,025,000,000 devices, which is a very huge number. It is very necessary that we try to solve the problems of IoT technology. So what are the problems that we concentrate during my internship? First of all, it's about the complexity. So the IoT devices are from different companies with different features, and they communicate with each other with different communication protocols, and all of these make the IoT networks very complex. The second problem is the rapid proliferation. So every day, the number of IoT devices is increasing. And the third problem is about the security threats. So I believe this problem is really important because the IoT network is not secure enough to be used in all the sectors. So according to these problems, researchers started to design and implement different monitoring solutions, and these make a visible increase in the number of monitoring solutions. So these monitoring solutions are mostly used to detect anomalies, detect threats, and detect failures. And the same process here is that all of these monitoring solutions collect data, analyze it, and find a pattern about the behavior of IoT devices. So there is a need for a generic monitoring platform, which can be a deployment platform for all of these existing monitoring solutions. This is what exactly I did during my internship. So let me talk a bit about the state of the art and all other researches that have been done until now. I categorized the state of the art of my project in two different categories. First, the monitoring function. So for example, one of the important monitoring function is anomaly detections. I reviewed many papers, and for example, there is one solution which is based on random forest algorithm, which can distinguish any suspicious activity with any normal activity. And in another paper, there is a solution which is two-layered architecture. In the first layer, they classify the traffic into ordinary and attack based on decision tree algorithm, and detect the attacks type based on random forest algorithm in the second layer. Another monitoring function is the device type identification. For example, Nesrine Amar, who was the PhD candidate in the same lab as me in Nokia Bell Labs France, designed and implemented the solution, which is based on decision tree algorithm and trained on 33 IoT devices. So in this platform, based on the first minutes of the traffic for each new device, and then analyze it, they can identify the device type. Or, for example, in another solution, again, for device type identification, they use data, but here from TCP stations. But in another category, there is a more general platform, a more general monitoring platforms. For example, ThingsBoard. ThingsBoard is an open source IoT platform which is now in the market. It can collect data, analyze data, visualize data, and even allow the users to manage different IoT devices. But it's not useful in the case of more complex analysis functions. So because the actually the analysis functions are predefined, so it cannot, it's for just very simple analysis functions. Another monitoring platform is Dynatrace. Dynatrace, again, it's a monitoring platform which offers a view across IoT ecosystems, and it can evaluate the performance and help the users to evaluate the performance of their IoT network and IoT monitoring platform. And they can, with Dynatrace, the users can collect data, analyze data. So it's very useful, but again, it's limited in the analysis functions because it's not programmable. It's there are some predefined analysis functions that this platform use, but it's not programmable enough to be capable to deploy and implement all the analysis functions. So based on these researches, we started to design a new platform for IoT network monitoring. We consider that this IoT network monitoring should be a generic one. So it should have different features, like as a first feature, for example, it should be scalable. By scalable, I mean have different IoT devices, have very complex analysis functions, or even have multiple analyses at the same time. So our solution for this feature was having hybrid solution. By hybrid solution, I mean have a cloud beside the network infrastructure. So the cloud is actually for analysis part, and the because analysis function is mostly very computing intensive, so it is better that we implement it on the cloud. And on the network infrastructure, we collect data and filter it, and then send it to the cloud to analyze it. Another feature for the one generic monitoring platform is supporting multi-tenancy. So multi-tenancy for here means that having multiple users, but without giving them access to configure or reconfigure the IoT network infrastructure. So for this challenge, we try to have tenant isolation, which means that we try to make the process from the first step to the last step very isolated, and to just not allow the users to have access to any kind of infrastructure out of their environment. And the third feature is the flexibility, which I believe was the most challenging for us. By flexibility, we mean that it can be used as much as possible in different use cases. So for this feature, we offer two different things. First is supporting passive and active monitoring. So by this, we can have different monitoring functions. And offering a platform which is programmable. So by programmability, we allow the users to program whatever they want as an analysis function and as a monitoring function. And by this feature, we overcome the challenges that I mentioned during the last part in the last two state of the art. So based on these features, we started to design the platform for monitor IoT network. We call it IoTNM, and here I'm going to talk about the architecture. So as you can see here, we have IoT network infrastructure, we have cloud, and we have one user who is mostly the system administrator. So he or she just wants to monitor IoT networks, collect some data, maybe analyze it, and find a pattern about the behavior, about different things about this IoT network. So in the IoT network infrastructure, we have different IoT devices. We have network equipments, which are responsible for connecting these IoT devices to each other and to the internet. And we have cloud, which is for the analysis function. So the system admin just sends the monitoring request to the orchestrator of our system. So here the orchestrator is responsible for management between the different communication between the different modules in our platform. And besides that, the orchestrator is responsible to create one analyzer per monitoring request. So after receiving monitoring request, it creates one analyzer, and then this analyzer deploy the observer on the network equipments and send the observation codes to all of the network equipments. Then the network equipments, based on the observation code, start to either traffic capture or probing the IoT devices and collect some data, filter it, and send back the filtered traffic data to the analyzer. So by this way, we avoid to mirroring the unnecessary data to the analysis part. Then the analyzer, as a second responsibility, starts to run the analysis code on the filtered data. And finally, it sends the report back to the system administrator or the user via the orchestrator. So here you can see the general view of our architecture. As you can see, we can have multiple analyzers here because it's a cloud. We don't have any limitation. And here we can have multiple observations at the same time in each network equipment. So after that, it was time to implement this architecture. So we use GNS3 as an emulation platform because GNS3 is really near to the real situation, real environment, as it uses Cisco equipment's images. And besides that, we use the different virtual machines and Docker containers. So this is the topology that we designed in the GNS3, and we wanted to map the architecture that we designed to this topology. So as you can see here, there are some IoT devices here. So they are busy boxes, which are the IoT devices. So actually, BusyBox is a very lightweight Linux-based VMware, which can just do very simple functions. So because of that, we used BusyBox in the implementation. And we have one switch, which is responsible for communication between the IoT devices, and we have one gateway, which is responsible for communicating the communication of IoT devices with the internet. And we have one user here who wants to monitor the IoT network. So this user just sends monitoring requests to the orchestrator. As you can see, all of these things are exactly the things that we developed, and the orchestrator here is responsible for actually creating one analyzer per monitoring request, as I said. This analyzer, for this analyzer, we use Docker container. This Docker container actually sends a first established connection to all the network equipments here, and then sends the observation code to all of them, and then waits for the results, which is the filter data from all of them, and run the analysis code and send back the results to the user via the same web interface. So here you can see the screenshot of our web interface. It's very simple but functional. So the user just submits monitoring request here as a blueprint. So this blueprint actually is the package of the code files that the user just submits, and then he or she can use one specific blueprint for doing different tasks. So tasks are the actually instance of each blueprint, and with specific parameters. And then the user can see the reports here in the same web interface. So after the implementation, we wanted to evaluate our platform and see how it works in different use cases. The first use case that we implemented with our platform was monitoring the incoming or outgoing rate. So by this, we desire to find exactly the rate for one specific device, and we categorize the process to two different parts: filtering process and analysis function. In the filtering process, it waits for the analyzer to send the target MAC address and object frequency, and then it detects packets with that specific MAC address and adds the packet's length to the total number of bytes and calculate the rate by dividing the total number of bytes by that update frequency. And then it sends the result to the analyzer. On the other side, the analysis function sends the specific MAC address which it receives actually from the user and update frequency to the observers. Then it waits for the rates from the filtering process, and then it sends the results to the user. Another use case that we implemented by our platform was device type identification. That was the PhD thesis of the Nesrin. So in this use case, we desire to find the type of each new device that connects to the IoT network. So in the filtering process, we detect new MAC addresses, which because actually for detecting the new IoT devices, we can detect it by their MAC address. And then we capture the first minute of outgoing traffic for each new MAC address, and then send the result to the analyzer. For the analysis function, we ask the observers to start capturing and verifying the new MAC address, wait to receive the first minute of their trace, run the analysis function, and then send results to the user. So as a conclusion, I will tell you the results of my internship. So we designed and implemented a monitoring solution which is very easy to deploy for all the users, adapted for all use cases, isolated for multi-tenancy, and scalable. And as a future works, we can implement it in the lab with real network elements and IoT devices to evaluate the performance in more real environment. We can implement different use cases, for example, federated learning, and we can have automatic feedback loops based on infrared knowledge that we collect from the IoT network. For example, we can have automated access control list updates based on the data that we collect from the IoT network, or we can have, again, automated load balancing. So these are the references that I used during my presentation, and thanks for your attention. If you have any questions, don't hesitate to ask.
Thank you, Pooneh. So now the floor is open for questions. Are there some questions in the audience? Yes, Marc-Olivier? We did not hear you.
Yes, sorry. Can you hear me?
Yeah.
Okay, sorry. So thank you, Pooneh, for the presentation. I was wondering if I am at home, I want to deploy your solution. How do I proceed? Do I have a new box to install in my home network? Do I have to upgrade my live box or my free box? So how do I proceed?
So actually, yes, we consider that this is mostly for the system administrator. So if we consider that you are the system administrator for your home network, yes, you can deploy it. But we didn't choose which platform of existing platform of a Nokia we can use for deploy it, but actually we want to deploy it in one of the existing product of the Nokia.
So, if I understand well your answer, you say that if my router at home is not a Nokia router, I cannot use it right now. Is it this?
If it's not Nokia, yeah, I think.
Okay. And second question, could you envision to deploy, say, a Nokia box aside, say, the legacy router, and maybe you have way to interconnect your Nokia box with this router to exchange enough information for your system? Is it something that could work or not?
Yeah, I think it can work because actually we consider that you just submit, for example, your monitoring request in our platform, and then we do everything, monitor data, analyze it, and send back the report to you. So yeah, actually we can connect our box to your router, get the traffic, do these things, and then send show you that report for you. Yeah.
Okay, and so I guess it was a bit short during your internship, but did you investigate functionalities exposed by existing routers?
No,
See how you could get
yeah. We can
information you could get?
Some routers that actually are strong enough in the computing things to deploy it. But yeah, actually, because of the situation, we didn't have time to deploy it in the real devices. Yeah, it's just in the implementation phase.
Okay, thank you.
You're welcome.
If I may, Fabio Pianese. Pooneh, what is the security model of your service, and how does it differ from, let's say, legacy systems such as, let's say, SNMP or Alto, in the way that information is accessed about things going on the network? Thank you.
Yeah. So actually, I think from SNMP is more for managing the network, but here we want to collect data and analyze it and find one pattern about the IoT network. So we give this feature to the users to just program whatever they want as an analysis function. So for the security, as I said, it's like because the whole of the process is well isolated, we don't give access to the users to have access to the environment around the process, and also because we consider that the system admin is responsible for using this platform, so it's not very in a very bad way. Because the system admin is the person who we trust, so we don't have the problem of security. But even in this case, because most packets are encrypted, we don't have the problem for accessing the data. We just use it for the packets which are we use the headers of the packets actually. Yeah.
Okay, so you say that there is no security issue because the owner of the thing is going to log into the software.
Exactly.
So,
the system admin of the network will have access to that.
And there is no network inactivity allowed to basically let remote access to the interface?
Even we didn't actually implement the authentication or this part for our platform, but for sure it needs to have the authentication process for each user who wants to submit one-time request, because we need to have a secure process. But again, I say that we consider that mostly the system admin who is trustable for us wants to use this platform.
Thank you.
You're welcome.
Time for one last question before moving to the presentation of Mélanie. Other question?
Yes, if I may.
Yeah.
I was wondering, is your architecture designed to install, say, software like, so for example, Fabio evoked SNMP, but you could also consider IP tables or Snort or this kind of thing, because you seems also to be interested in controlling network activity. So is your network architecture designed to embed this kind of software, or is it more complicated to deploy new features?
No, it's not. If you mean, I'm not sure that I got it in the right way, but if you mean that we can add some features to our platform, yes, we can. I mean,
it was my question, but actually the question was rather in which form. So for example, is it, say, a Linux package or something like this?
Okay, I didn't understand. Can you repeat your question? Sorry.
My question is, how can you deploy a new feature on your architecture?
Oh, that okay. Okay. If we have, for example, new feature, actually the platform now is programmable. So as a new feature, if you mean new analysis function, yes, it is possible, because actually we just submit code files, so you can do whatever you want with our platform. But as a feature to our architecture, I don't think so. Yeah.
Okay, so you have to conform to a kind of syntax and to be a programmer to be able to deploy a new feature, if I sum up.
Yeah, exactly. Okay. But again, for non-professional user, it's usable because actually we consider, for example, one library of different functions which are predefined and non-professional user can use. But if they want to change something, yeah, they should be able to program that.
Okay, thank you.
You're welcome.
Okay, thank you, Pooneh, and thank you to Marc-Olivier and Fabio who asked the question. Now I think we can switch to Mélanie.
Okay, let me share my screen.
Yeah.
Okay, can everyone see it?
Yes.
Good. Well, good afternoon, everyone. Today I'm going to talk to you about summarization. So first, I'll give a bit of an introduction on the subject and talk about our proposals. Then I will take some time to present how it works and how our different proposals work. And if I have time, I'll talk to you about the evaluations we made, and then I'll conclude. So first, why do we need summarization? Well, there is a lot of data available online nowadays, and it's very tedious to look for specific information, and it can be very time consuming. And well, learning depends on the learner. So writing a summary can be quite complicated, and also learning can be critical, and this is why we really need to address this problem. So existing solutions exist. For example, you probably know Wikipedia or Stack Overflow. They're really well known. They allow you to see a kind of overview on a big amount of subjects. So it's universal, it's free access. It gives you structured information, so it enables you to focus on a subject that you want to have information about. But the main issue is that it is human-made. So we need people to write those summaries, to answer questions on Stack Exchange or Stack Overflow. And it might be actually subjective, and it takes time to write them. So there also are solutions to produce automatic summaries. So this addresses the problems from the previous solutions. It's necessarily objective and it's automatically made, so no human effort anymore. But the main problem of existing solutions is the lack of adaptability of summaries, then sometimes not easily readable, and they're not efficient on really big data sets. So what we are proposing is a solution that can produce automatically summaries, that produces structured summaries that are query-based and interactive to be able to really focus on a subject, and a solution that is scalable. So we really want to cover huge data sets. So here is our first proposal. It is a summary in which you can expand each sentence to get more details on the subjects it's addressing. So for example, here it's a summary made on the query pangolin on a dataset of Wikipedia animal pages. And only the two first sentences are the basic summary. And it's just basic sentences, general ones on pangolins, but then the second sentence has been expanded. And you can see sentences 3 and 4 are a sub-summary produced from the second sentence, and that give details on the subject of the second sentence, which was the diet of pangolins. And now if we do that again, and we can do it again, we can expand the second sentence of the sub-summary to get more details on insectivores, which was the subject addressed by this sentence. So these solutions are good to focus on a subject and to go deeper into a subject, but the main issue is that we might not cover all the subjects that are addressed in the data set we are trying to summarize. So the solution we found was to produce a structured summary. So here you can see a very basic example because we didn't have much space, but we have a document that's produced from the query bird on the same data set, and it's organized in 2 sections, and each section addresses a specific theme, and this theme is defined by keywords. So the first section is associated to the keywords wing and flight, the second bird and nest, and etc. And in each section, you have sentences summarizing the section. And we also produce summaries that have subsection. And in that case, we would have a summary for the section, and then we would have subsections, each containing text addressing the theme of the subsection. So how do we actually do all this? Well, to produce hierarchical summaries, so those summaries that have structure, we first need to build flat summaries. So to build those, we need 3 main steps because we are going to use extractive summarization. So the purpose of this method is to extract relevant sentences to produce a summary. So first, we need to represent lexical units, which means we need to represent text, sentences, and words in a way to use them in our model. Then we will need to compute scores for sentences, and these scores will be computed thanks to the representations that we build. And finally, from the scores on the sentences, we select sentences. So with higher scores, ordering them, filtering them. So how does it work? Well, first, to make our method faster, we're going to extract the best documents to then summarize them. So we have documents, and we will compute weights for each pair of document and word, so that each word can be represented by a vector on documents, and each document can be represented by a vector on words. So that is called the embedding, and the weights we use are computed according to frequencies of the words in each document, in the data set, and also on the length of documents. So to do this, to compute the embedding, and then to proceed to the next steps, we are going to use a tool called Gizmo. Probably lots of you heard about it. Once we are done with building the embedding, we can see it, we can view it as a graph on documents and words. So we have a bipartite graph between documents and words, and this graph is weighted with respect to the weights that we computed just before. So there is a vertex between a document and a word if the word is contained in the document, and there is the corresponding weight on the vertex. And on this graph, we will be able to use a ranking algorithm, very similar to the one used like Google, which is PageRank. So the one we used is called de-iteration, and it consists in putting fluid on the graph and let it spread on the graph from the query words. And so once we ranked the documents, this ranking algorithm gives us a ranking on documents, but also a ranking on words. And we will use the ranking on documents to extract the best ones. Once we have the best documents, we will proceed exactly in the same way for sentences. So we have sentences, we build an embedding, which is the representation step we talked about earlier. Then from these sentences, we build the graph, we proceed to the ranking, and the rank of sentences will be what we will use as score. We don't use the ranks as scores, but the probability that are given by the ranking algorithm. So each sentence has a score, and we keep the best ones. So once we have those sentences, we don't build the summary directly from them. We process them with a tool called Spacy to make the summary more readable. So here what we do is filter non-verbal sentences because they don't bring information. We delete adverbs at the beginning of sentences because it's very unlikely that we select two sentences that are following each other in the same document. And so, however, or hence, at the beginning of a sentence might be more confusing than anything else. So we just delete them. And then we proceed to co-reference resolution, which is replacing a pronoun by the noun it stands for, so that a sentence is standalone and really speaks for itself. And once we did that, we can generate the summary from the processed sentences. So now, how do we build our hierarchy of sentences? Well, we just produce a flat summary, as I just explained, and then we use exactly the same process, but with a different query. So remember, we diffused on the graph from the query words, and that's how we used our query to produce a summary. Well, now to produce a sub-summary, we'll use an expanded query that contains the sentence whose subject the sub-summary will address. So, for example, this sub-summary will address the subject of this sentence because this sentence will be added to the query to make it specific. And the same for this sub-summary that will address the subject of the red sentence, same for the green, and then we can do it again and again and again and go as deep as we want to produce more details on the subject. So now, as we saw earlier, it might not be enough to cover the entire all the subjects addressed in the dataset. If we want to summarize a dataset and cover all the themes and present all the themes inside this dataset, we need to produce a document structured into sections and subsections and be able to show all the themes that are addressed. So first, we need to build a hierarchy of words that will allow us to build the sections and the subsections and organize our document, and only later will we produce text to fill this structure. So the extraction of keywords will be the same process as the extraction of documents or sentences. So why do we extract keywords? Well, we don't want to use the entire, I don't know, 80,000 words of a dataset to produce a structure. It would be way too much. We want only the useful keywords of the dataset. So we take the documents, again, we build the embedding, we build the graph, we proceed to the ranking, and we get the keywords, the words that have the best ranks. And then from these words, we build the graph. So this graph is first a complete graph, and then what we do is we compute the cosine similarities between words. So remember, the words are represented by vectors on documents. And so what we do to compare words and to know how similar they are to each other, we compute the cosine between those vectors. And so we get a graph and we delete the vertices on which the cosine is 0. So for example, words that are not at all in the same documents, that have no documents in common. So we get this weighted graph of words, and now we want to identify themes and sub-themes inside this graph. So what we do is we proceed to a clustering algorithm, and the clustering algorithm we use is called Louvain, for those who know it. And what it is, it's an agglomerative clustering algorithm that is based on modularity maximization. And what it does is it produces a hard clustering at the end. So here we produce a first hard clustering. So we have two sections here, the section in blue and the section in red. But we don't stop there. We can go on. And for example, we can cluster again. The red cluster can be partitioned again to get subsections inside. So we apply the clustering algorithm again on the red words, and we get two clusters, the orange one and the yellow one, and then we cluster the blue cluster, and so on. And we could go on the green and on the orange, as long as there's more than one word in the cluster. But we don't want to go too deep because we want the document, again, to be readable. So if you have subsections, it might not be readable anymore. So from there, we have a hierarchy of keywords. As you can see there, you have all the keywords at the top. Here it's just 10 for the purpose of the example. Then you have the sections, which are the children of the root. And then you have subsections. Now what we want to do to produce a document is produce text for each of these clusters and each node of this tree. And to do so, we need to represent each cluster by a vector that we will call a centroid. So basically, the centroid is a vector on words that will represent the cluster, depending on the words that it contains. For that, we use the TF-EDF weights. So if a word is in the cluster, the coefficient is the TF-EDF weight. And if the word isn't in the cluster, the coefficient is 0. And we get a vector for each cluster. And then to generate the flat summaries, we use a score that's a bit different from before. So if you remember, for flat summaries, we used the result of the ranking algorithm as scores for our sentences. Here, we will use a similarity between the centroid of the cluster and the sentence that is evaluated. We use this specific score to be able to choose specific sentences that will really represent a cluster and one represents more a sibling of the cluster. So what we do is we use as a score the similarity between a sentence and the centroid of the cluster that we want to summarize, and we correct it by removing the similarity between the same sentence and the siblings of the cluster that we want to summarize, so that the extracted sentences really will be specific to the cluster. And so now we just have to go through the entire tree, produce a text for each cluster, and we get a document as we've seen earlier. So evaluations, do I have 5 minutes for evaluations?
Yes.
Yes? Okay, so we compared our summarizing technique with text rank, the flat one. So why text rank? Because it is an extractive summarization method, so it's quite comparable, and it's available online on GenSim, a Python library, and it's one of the few that is actually accessible freely and easily. So we used ROUGE scores. Those are scores comparing the words that are in a generated summary we want to evaluate and in a reference summary that is given. So to build these curves that you can see, we needed a text rank summary, a summary generated by our approach, but also a reference summary that was given. So these have been produced from a dataset of scientific articles. And the reference summary was the abstract of the article, and the summaries were produced from the content of the article without the abstract. So here, as you can see, it's a cumulative distributive function, which means, for example, the probability of getting a ROUGE score that is less than 0.4 will be 40%. Okay, which means you have a 60% chance to get a score that is higher than 0.4. So that's how we read it. And we can see on this curve that we are quite equivalent to text rank. On ROUGE, we used also cosine similarity. So as I explained, we have each summary that can be represented as a vector on words, again, coefficients being the TF-EF weights. And we can compare two summaries by computing the cosine between the two vectors. And again, we compare text rank to a reference summary, and we compare our approach to a reference summary. And again, we get quite similar scores. It's quite coherent. The real difference is between computation times. So we computed summaries of 100 documents. So it's still, the same scientific articles. And we tried to summarize 100 documents. And we did that a few times, computed a mean. So our approach takes approximately 21 seconds to build the summary of 100 documents, whereas text rank takes more than 7 minutes on average. And here you can see the times, the cumulative sum of execution times between our approach and text rank. So conclusion, what did we do that for? Well, what we want to do is facilitate the process of learning. We want to make learning free, fast and easy, and we want to be able, for example, to generate state-of-the-art automatically, and it could allow us to dive into product documentation quite quickly as well. What we did was proposing methods to generate structured query-based summaries or interactive query-based summaries, depending on if the reader wants to really focus on a detailed subject or wants an overview of the dataset that is summarized. What we want to do next is maybe explore a abstractive production of texts. So from the sentences that are extracted, they're not really coherent yet, even though we semantically process them. So it would be interesting to use a neural network, for example, to produce a coherent text in natural language from the extracted sentences. What we could do as well to summarize very, very large data sets would be not producing one document, but producing an entire set of documents. And this set could be, there could be links between the different pages to be able to go from one to another and have pages built in sections and subsections, as we've seen, a bit like Wikipedia, but that would be automatically produced from any dataset. Before I'm done, I'd really, really like to thank my two tutors, Marco and Fabien, because they really, really helped me a lot for this presentation, for my report, and for my full internship.
So thank you, Mélanie. Any question in the audience?
Yes, I have one. Can you hear me?
Yes.
Yeah. Okay. So the input text is written by humans.
Yes.
So when you evaluate your tool, you evaluate it against an abstract that is written by humans.
Yes.
So both are subjective. So why do you say that your approach is objective?
Okay, the approach is objective in a way because you use many documents to build a summary, and it's not written by one person. You will take sentences from one document and then from another document, and so there won't be one person with one opinion and point of view that wrote the summary. But it is true that the evaluation is really tricky and actually not objective at all, because we evaluate against an abstract, but it's not probably the only good summary that would have been produced or that was possible for this document. So it's very tricky. It's like we can evaluate against one humanly produced summary, we can evaluate against different summaries that have been humanly produced, but it's very difficult to get an objective evaluation of the production.
Sure. That is also related to a second concern. So you raised it actually. So suppose you have on a topic two sets of documents that are completely contradictory with one another. So your tool is maybe likely to favor one over the other.
It is. But if the same amount of keywords are used in both, it might even take sentences from both and say one thing and the exact opposite in summary.
So if the human writer of one of the input documents knows how it is going to be processed, he can put his view up to the summary, even if it's a very small subset of all available documents.
You mean by using more keywords?
Well, if he let's say that he first has your algorithm, and he can extract what are the important keywords.
Yes.
So then he can use those keywords on purpose in order to boost the text he writes into the summary you generate.
Yeah, well, it is possible, but for example, we treated datasets of over 30,000 documents. To have one document being completely biasing the result, it would have to contain really, really a lot of keywords. And it would have to be a really long document and really awkward, I think. It might be difficult to read because it contains so much of the keywords and the sentences might be really awkward, but it's possible.
Sure. Don't forget that such documents maybe are not written by humans, just generated. So, okay, that's all for me. Thanks.
Other question in the audience? So maybe I have one question. So for people external to this work, we see that there are different steps for the processing to get at the end the structure summaries. Mm-hmm. It may seem, but it's not easy to do it. I know it. It may seem that there are some ad hoc solutions that are used. It may seem sometimes a bit fastidious. What drives you to produce the solution with these different steps? What are the inspiration? What are the ideas behind that make you to follow the steps that you follow?
Okay.
Just to understand.
Okay, so why did we choose extractive summarization and why did we choose clustering and things like that?
Yeah, and the way also to do it sometimes.
Okay. So what we decided was that we wanted something that generates summaries of very large data sets in a reasonable time. So we chose fast algorithms and algorithms that were quite reliable. So for example, if we had used neural networks for producing the flat summary, it needs time to be trained, even though it's unsupervised training, which is sometimes possible. And it would take time to produce the summary. And even though it's most of the time producing good outputs, there's no guarantee that there's no minimum guarantee of the quality of the output. So using a ranking algorithm and an embedding with TF-EDF weights was a way to represent documents and words quickly and to rank them really quickly, to be able to extract sentences in an effective way. And then for the clustering algorithm, it's a bit the same thing. We want quickly to identify themes. And so we extract keywords with the fast algorithm we used for sentences. And then we use this clustering method that is quite effective to identify the themes. Also, we used this clustering, this hard clustering, and then clustering again, the different clusters. And we didn't use directly a hierarchical clustering technique because we wanted to produce a structure that was close to the structure of a document. And if we use a hierarchical clustering, it sometimes gives a structure that is too deep or that will often isolate one word on each step and things like that. And so it gave better results to have this divisive algorithm, and that takes us to the depth that we want to get.
Okay, thanks. Other question? So maybe I will ask a last question. It's more for the future. What is planned for the future of this solution? In fact, what kind of usage will it be used? Are there some plans to use it for which purposes? General question.
I gave general ideas of how it could be used and what we could do with it. The purpose would be being able to build automatically a Wikipedia, so navigable pages going from one to the other and having pages on specific subjects and things like that. And it could be used for plenty of things, anywhere that we need to learn or to learn quickly or more effectively. It could be used by students, for example. It could even be used by teachers who need to dive into a new course before starting. It could be used for generating automatic state-of-the-art, as I wrote, because when starting on a new subject, it can be quite long and tedious and difficult to produce a state-of-the-art. So you could help doing all these things. But we don't have a a concrete application right now that could be implemented like in a month or two.
There was this one written in your conclusion, diving into product documentation. So maybe I was thinking that you have some more ideas about that.
No, not precise ideas.
Okay. Okay, thanks. So thanks, Mélanie. And thanks, Pooneh, also for your first presentation.